It has been 51 years since Apollo 11 landed on the moon, making Neil Armstrong the first man to set foot on the moon. Now there has been a shift in focus for space exploration. New technologies have enabled multiple countries and industries to begin exploring Mars. With a race to put humans on the surface of this planet, there are multiple challenges that will need to be faced. If humans are to stay on Mars for a significant amount of time, they will need to have their supplies replenished. NASA's Martian Integrated Terrestrial Environment for Exploration and Research team are looking for a prototype for a Mars cargo rover, which will transport supplies from payload landing sites to MyTier camps. We are Team 10, and here is our macro prototype proposal. With working on a new territory, such as the surface of Mars, there are many things that need to be taken into consideration when designing and building the rover that will transport cargo across the terrain of Mars. The four main objectives for this prototype design for the macro were to precisely navigate to various sites, handle hazards that come between itself and its destination, work in transporting payload in a timely manner, and transport cargo without letting it tip or fall before the macro reaches the delivery site. The macro should do all of this while being both efficient and safe.
When it came to project management, our team had broken down this project into achievable components through the usage of various methods. Our team in the first meeting had started by breaking down the components of the macro using the work breakdown structure. This allowed us to look at each component of the macro, being building, coding, and testing, and develop an understanding of what needs to get done. Using the work breakdown structure, our team was able to develop a Gantt chart, giving us a flexible yet structured schedule of what was going to go on for the coming months. This allowed us to set certain meetings on certain days and helped us keep on track in order to not fall behind on the schedule. The Gantt chart also allowed us to divide up work and come to meetings prepared with what needs to get done. This allowed for meetings to become more focused on major topics instead of wasting time on coding or building just one part. However, when it came to dividing work, even with the Gantt chart, this was a problem because of our online teammate. She did not attend any of the pre-planned meetings and did provide little input towards the project as a whole. The rest of the team had to pick up the work that she was supposed to do, but we were able to complete the task on time due to our ability to properly time manage and divide up the work appropriately. The Gantt chart shown represents the schedule we had created with the belief that the demonstration was going to happen on November 9th, not November 16th. But by planning ahead and giving us a spare week of time, it became very beneficial. Our use of the Gantt chart and ability to plan ahead was very useful because of the fact that our GrovePy had stopped working due to a library issue. We were able to schedule around this issue and still develop progress on our macro through building and documentation aspects. The building aspect came after, however, we were able to define the engineering specifications for our macro and set target values on what we wanted our macro to achieve. By defining these engineering specifications, we knew the bounds that we could develop ideas about different parts of our macro. This led us into the brainstorming process, where we made each teammate use at least one of the different methods to develop ideas for our macro. Then we all came back together as a group and decided on general ideas and concepts that we believed our macro should have. This allowed us to have multiple point of views on how macro should be built and what general ideas that we all agreed on. This allowed us to create concepts about the different components of the macro and start building the macro. From the brainstorming portion, our team had all agreed on an elevated base that everything would be attached to or supported on. Our team then moved on to means of movement for our macro. The three ideas were a standard four-wheel drive, a three-wheel drive with a lone wheel in front, and a two-ski, two-wheel drive with the wheels in the back pushing the macro. Using the decision matrix, the ideas were compared against each other, and the ski idea achieved the highest score, mainly because the skis would have the lowest friction against the paper, making when the macro was making line adjustments, turning would become a lot more smooth. The four-wheel drive could provide more speed power, but the friction between the wheels and the ground would cause too much trouble for the macro when it makes line adjustments. The three-wheel drive suffers the same problems as the four-wheel drive, but also provides less speed power than a four-wheel drive. The next component of the macro that needed to be built was the cargo system. We all came up with 3 separate designs for a cargo system, each with different methods of delivering the payload. The 3 designs were a spinning arm that would hit the payload off the back of the macro, a conveyor belt that would move and bump the payload, and a lowering ramp that would allow the payload to slide off the back of the macro. Again, our team used the decision matrix, and the lowering ramp was the best option out of the 3 because its ability to perform each task was average compared to the other concepts that excelled in one area but fell short in others. Our team tried to build a lowering ramp for the macro, but we were unable to build the ramp due to the gear system not meshing properly, causing the ramp not being able to rotate down. This caused us to use the spinning arm idea, as this was the next best optimal option. We started to test our macro using the different example maps given by the instructional team and came across the problem of our macro not being able to move up the hill portion of the course. This made us decide to choose between a front wheel drive and the original rear wheel drive using a decision matrix. In the end, the front wheel drive was comparatively more optimal due to the wheels in the front being able to climb the hill 5 out of the 5 times compared to the rear wheel drive being able to climb the hill once. Based on this information, we were able to make a decision on which drive was the most optimal version. We used these different decision matrices to provide the most optimal concepts for our macro, and this allowed us to design possibly our most optimal version of a macro that we could.
For the programming behind the macro and its delivery system, there were 2 main Python program files. For the main demonstration, a single Python program consisted of a series of conditional statements that would determine how the wheel's motors would move. The first condition it checks is to see if the Hall sensor is getting a value of 0 or 1. If it is getting a value of 0, then it implements the algorithm regarding the magnet sensing. It keeps account of the number of magnets it passes, and if the magnet count is equal to the drop-off variable, which is input by the user based on the site they specify, then it turns onto the break-off path. When the magnet count is 1 more than the drop-off variable, then it implements the motor movement for the swinging arm to knock the cargo off of its platform. When the Hall sensor is not sensing a magnet, then the program iterates through the elif statements regarding the line finders. When the line finder on the right side of the macro detects a black line, the right wheel moves backwards while the left wheel moves forward, and vice versa for when the line finder on the left detects a line. This was intended to make sure that the macro follows the line closely. For the speed test, initial testing found a correlation between the speed of the macro and the power of the motors. Based on a graph, an equation of the correlation can be used to calculate the power the motors need to be in order to reach the specified speed. Using an adder variable, which is 1/20th of the target motor power, this program increases the motor power by adder every 1/20th of the time it takes for the macro to reach the specified speed within 50 centimeters. Once it reaches top speed, it keeps track of an elapsed time variable, which will increase until it reaches 200 divided by the target speed, which signifies that it has traveled 200 centimeters at the specified speed. The adder variable then is flipped to a negative and added to the motor power until the macro has decelerated to 0 centimeters per second. When our team ran into issues with the GrovePy, which were consistent across multiple weeks of the project designing process, we had minimal time to write the programs for the macro. However, within the remaining weeks, we were able to formulate the programs, which initially used light sensors to manage the line following, but this proved to be inefficient in the presentation of competency, as the light values varied all across the room. Replacing the light sensors with the line finders was a simple fix, and based on testing on sample tracks, the macro should have worked properly in the final demonstration.
It's so long that once you start lower speed, right? Okay, it's not one.
This is so aggressive.
Moving on to the attributes of the macro we designed, our design contains many beneficial attributes to help it tackle the tasks at hand. A major positive is the simplicity of our dropping system. The cargo can be loaded easily into its open top. Once it reaches the destination, the attached motorized arm then rotates and gently pushes the cargo off onto the drop-off site. This method has been fairly accurate too, with the dropping accuracy being 4 inches from the center of the drop-off in our testing. The simplicity also decreases the chance of malfunctioning because it does not complicate itself with unnecessary parts. Another beneficial design element is the front-wheel drive motors. We knew that the terrain the macro would be on would be rugged. The front-wheel drive tackles this problem by pulling itself over the obstacles, which from our testing proved to be easier than pushing over them with the rear-wheel drive system. The decision to make our line sensors close to the same width as the line was also another positive for our macro, as it was made pretty wide already, so by placing the sensors close together, it allowed us to stay very close to the line being followed and not run off course too far. However, moving away from the positive attributes of our design, there were some negatives that we realized our design had. One of those being that it is not very well structured in the way the cargo held tight. In testing, it worked fine going over a small obstacle provided, but we worried that obstacles on an uncharted surface could prove to be a bigger problem. Another negative attributes relate to our code. It was partially hard-coded when it senses magnetic locations, so it turns at a certain angle every time. So if the drop-off angle is different, it won't properly turn back onto the track. And finally, to make sure all our Hall sensors work correctly, we had to keep them low to the track. The problem with this, however, is the sensor hits obstacles, and in the testing, it even ripped it off the body once. These negative attributes all have the ability to be worked on in the future, and we plan to fix them. Coming from the negative attributes, we are able to work into the areas of improvement regarding the macro and its design. First, we had focused on obstacle clearance so that going over an object would not pull pieces off the macro, which is what happened to us during testing. This problem would be fixed by using more elevated design so that the Hall sensor would not be in the way of obstacles. We would also improve the line sensing and making it more secure because the sensors would sometimes move or bounce, becoming uncalibrated with the ground and leading to the macro getting off track as seen in our testing. This would greatly improve the movement aspect of the rover if we were to get this fixed. We would also work to make the bot more autonomous with the removal of some hard code we would use in the turning to get onto the drop-off location, which is done by using the sleep function repeatedly and putting in the angle of the drop-off. Finally, as a group, we would restrict last-minute changes. This was something we did, and we all agreed that it did not help us and in fact hindered our project. The biggest of which being the switch from the rear-wheel drive to front-wheel drive, which we believe to have messed up our line following and sensing code. We were not able to test these last-minute changes, which led to them failing in the end. In conclusion, there's much to improve on to perfect our macro, but we are proud of what we accomplished. We had many ups and downs throughout the process, whether it be the GrovePy library not working for us for 3 weeks, to our online teammate dropping the class and leaving us down a member. Through it all, we came out with a functioning macro, able to drop off cargo and perform. We hope to use the skills we learned here to progress farther on to the next project and to perfect our designs. But as for this project, the next step will be to present our results and prototype to the NASA Meteor team and get this rover onto Mars.